In pursuit of sharing technical knowledge and just to gear up the new generation of engineers, myself, Pranab, is here to deliver today's presentation, Power Transformer Part 26. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with design perspective of terminal bushings. Basic requirements and aspects are to be considered while designing any type of electrical bushing. A. Dimension and size of the central conductor must have to design with considerations as on the rated load current and the fault current to carry at the event of system short circuit. Number B, it has also to be taken in account that the surrounding insulating material of the central load flowing conductor should have to withstand all sorts of electromechanical stress and strain during overheating phenomena at the time of occurrence of these short circuit events. The nominal operating and occasional transient electrical field stresses as developed due to the potential differences between the live conductor rod and the grounded external surroundings are thus to have a direct impact on the bushing's internal insulation. Most important. D. Occurrence of partial discharges once would have been started that may have to instigate progressive deterioration of bushing insulation part. E. Therefore, constructional features of bushings internal insulation unit must be so effectively designed and manufactured that the internal surface would always be able to restrict the inception of partial discharges. If so far the bushing's external insulation is concerned, adequate dry arcing length should have to be configured so as to make it much effective for withstanding the unusual lighting strikes and switching impulses. G. Moreover, the rain shades or water shades as provided on the external surface of the cylindrical glazed porcelain bushings, which should have to be designed in such a way that the available creepage distance would have become sufficiently adequate. H. Adequate creepage distance would have to be maintained to prevent excessive flow of leakage current, which has to produce from a combination of dirt with accumulation of ambient moisture. In the case of bushings, creepage distance is the distance between the bushing top metallic dome or terminal and the flange, which is referred to in terms of millimeter per kV. Based on the pollution level of the location where power transformer are to be installed, customers may have to specify their appropriate requirement for the creepage distance of the bushings, which is as follows. Pollution level, heavily polluted atmosphere, design creepage distance is of 25 millimeter per kV, and very heavily polluted atmosphere is of 31 millimeter per kV. It might have been more than that of 31 millimeter per kV. Okay, as a basic criteria for any given transformer, the current carrying central conducting rod of a low voltage side bushing has obviously to carry a higher range of current than its high voltage counterparts. Therefore, the central conducting rod of a low voltage bushing must have always of a larger diameter than that of its high voltage counterpart, as because low voltage side current is much more than that of HV side. As of standards IEC 60137, bushings are thus to be installed in power transformers with having maximum of 45-degree inclination of the vertical from voltage class of 72.5 kV to 420 kV and a maximum of 30-degree inclination of the vertical for voltage class of 550 kV to 1050 kV. Possibility to use bushings inside extreme weather condition. So, bushings cantilever strength should be high enough to cope with the anticipated mechanical stresses that will also be acted upon the bushing during seismic and short circuit events. Possibility, again I repeat, possibility to use bushings under extreme weather conditions. So, bushings cantilever strength should be high enough to cope with the anticipated mechanical stresses that will also be acted upon the bushing during seismic and short circuit events. Low voltage side bushings are typically of solid type bushings which are being encased with porcelain or composite resin silicon rubber insulator. While designing of high voltage side bushings, it is of much importance to frame out the bushings constructional features as well as their basic characteristics with the appropriate capacitance rating for that typical voltage class only. Capacitance graded bushings are therefore be completely different from the basic constructional features of solid type bushings and that to be explained later on. Now, list of major types of transformer bushings which are to be fitted as per voltage class and current carrying criteria. 1. Solid bushing. Number 2. Composite bushing. Number 3. Compound filled bushing. Number 4. Condenser bushing. This is also of 3 types. One is resin bonded paper bushing, oil impregnated paper bushing, and C. Resin impregnated paper bushing. Then number 5, dry type bushing. Number 6, oil filled bushing. Number 7, oil immersed bushing. Number 8, oil impregnated paper insulated bushing. Number 9, resin bonded paper insulated bushing. Now let's discuss with solid bushing. A transformer bushing is an insulating component that provides a safe path for current carrying conductor to pass through the grounded tank of the transformer. Thus, bushing has to act as an insulating barrier between the live conductor and the metallic, that is conducting body of the transformer, or any of the electrical apparatus lying at ground potential. For low voltage and medium voltage applications, a typical non-capacitance graded bushing product, which is completely solid in construction, could have been made by porcelain, epoxy, or silicone materials conforming to standards established by the IEEE, that is Institute of Electrical and Electronics Engineers. Among the insulating materials, porcelain is widely used as it offers mechanical sturdiness and a long service life. But the application of polymeric type of material like silicon rubber is becoming much more acceptable as an insulating material due to its lower cost, ease of handling, and its special characteristics of surface hydrophobicity. See the diagram. Here is the copper conductor threaded at both ends with nuts and washers, sealing gaskets, cap which is meant to center the copper conductor and into which top end of the insulator is cemented, water sheds, porcelain insulator, transformer tank mounting flange, dashboard washers, spring washers, clamping nut, etc. etc. The superior contaminant of surface hydrophobicity would have to restrict the basic formation of conducting water tracks, and for which that has to limit the possibility of surface leakage current path, and at the same time also to counter the risk of pollution related flashovers while used in outdoor environment. So the most important criteria to use as bushing material is that the surface of silicone rubber has excellent water repelling properties and has an ability to control the state of leakage current fairly well. Porcelain bushings have the possibility of becoming pressurized, fragile, and prone to extensive damage when impacted by high velocity projectiles, which supposed to be a major incidental failure of the equipment itself. Based on the withstanding ability of bushings, internal insulation as corresponds to nominal operating voltage stress, as well as occasional transient electric field stresses, it is recommended that up to 11 kV voltage class solid porcelain insulation would have to be safely used. Now, number 2, composite bushing. While bushing whose insulation is composed of multiple coaxial layers of different insulating materials, then such type of bushing is termed as composite bushing. Composite insulations are thus to be compiled of at least two insulating materials, of which one material is providing high electrical resistivity, that is electrical properties, and the other is to provide certain mechanical properties just to withstand the mechanical stresses. The manufacturing process of combined insulation bushing is as follows. A centrally placed conductor rod is primarily be molded with a direct layer of an organic insulating resin by applying vacuum resin impregnation and temperature curing processes. Resin layered conductor rod is then to be encased by the process of molding with a silicon rubber insulator. The silicon rubber insulator, which consists of a single self-contained piece, is thus to be molded to form the desired dimensions and basic geometry of the bushing's rain shade profile. Most important. Moreover, the resin layered conductor rod that would have been protected by the silicon rubber insulator from the inclement ambient environment. Composite resin silicon rubber insulator is broadly introduced as an effective alternative to porcelain insulators because of its lower cost, ease of handling, and moreover, it exhibits a high level of hydrophobicity, which helps to decimate the actual risk of pollution related flashovers. Materials which are naturally repel water, causing droplets to form, are known as hydrophobic. Hydrophobicity is the association of nonpolar groups of molecules in an aqueous environment which arises from the tendency of water to exclude nonpolar molecules. Hydrophilic characteristics are just opposite to hydrophobic phenomena. Hydrophilic materials that have a special affinity for water and their surface would have a tendency to cause water to spread out evenly. The hydrophobic surface is therefore be of water repellent in contrast with a hydrophilic surface that is easily wetted. Even under the severe environmental pollution conditions, these hydrophobic characteristics of silicon rubber would have to suppress leakage current. Typical value for hydrophilic porcelain is 10 milliampere, and for silicon rubber it is less than 1 milliampere. This particular phenomenon of suppression of leakage current may lead to restrict the most unacceptable discharge activity of the bushing's surface, and for which bushing material erosion problem would have been drastically reduced. In present context, composite resin silicon rubber insulator framed bushings are commercially available for voltage class up to 72.5 kV and obviously has to provide several advantages and also some disadvantages over oil-filled porcelain bushings. Now, advantages over porcelain bushings. As the surface material is of silicon rubber and the composite bushing manufacturing technology that has been so precise that the surface including rain shades and sheaths is virtually made to be free of voids and also may have less chances of imperfection. Of the same voltage class, the weight of the composite bushing is rather 10 to 20% of the weight of porcelain bushings. Of the same voltage class, the overall length of the composite bushing would have been shortened by more or less 10% than that of the porcelain bushings. As because silicon rubber has the characteristics of hydrophobicity. So, in the same ambient environment, the composite bushing has the better self-cleaning performance. Thus, less deposition of conducting dusts on the bushing surface may ultimately help to restrict the flow of leakage current, and for which possibility of flashover can also be avoided. Flashover due to pollution or dust accumulation on the rain shades or in the surface of the silicone bushings, rubber bushings. Silicon rubber is a polymer having elastic properties and in the form of a polymer. The silicon is derived from the constituents of silicon, carbon, hydrogen, and oxygen. Basic characteristics of silicon rubber. A. Usually has poor thermal conductivity. B. Excellent heat resistance property. C. Thermal stability over a temperature range of minus 60 degrees centigrade to plus 250 degrees centigrade. D. Low in toxicity and chemical reactivity. E. Practically, ozone has no effect on silicon rubber. F. Ability to repel water. G. Excellent oil resistant property even at high temperatures. H. Rarely affected even at long-term exposure to UV rays, winds, or rain, but have a poor abrasion resistance. Superb electrical insulating properties with high dielectric strength, which typically have a volume resistivity in the order of between 10 to the power 14 ohm centimeter and 10 to the power 16 ohm centimeter. Silicon rubber surface is intrinsically hydrophobic, and that hydrophobicity can have to migrate at the pollution layer as deposited on the surface of silicon rubber insulators. The loss of hydrophobicity for the surface pollution layer would have to depend on the chemical structure of the pollution layers. For polymeric or non-ceramic insulators, the hydrophobicity loss or reduction would have to instigate significant reduction in electrical insulation, which has to influence ongoing aging process of insulators. In case of silicon rubber insulators, any change in hydrophobicity properties are of much importance as because it is literally been established that the component of surface leakage current is directly proportional to its hydrophobicity loss. While being exposed to outdoor environmental conditions, and particularly during worst phase of humid atmosphere, that is rain, if the high voltage silicon rubber insulator that has to undergo severe type of electrical stresses as established due to have prolonged exposure to corona discharge activity, then its surface hydrophobicity properties would have been mutated to hydrophilic properties. Over a significant time gap after diminishing corona discharge effect on the insulators, these reduction of hydrophobicity would have been gradually recovered. However, the time required for recovery of hydrophobic properties must have to depend on the composition as of silicon formulation. Usually, for HV outdoor installation, the silicon insulating materials are mainly from polymers which composed of high consistency with perfectly heat cured polydimethyl siloxane, that is PDMS elastomers. Polydimethyl siloxane PDMS elastomers. Reasons for which polydimethyl siloxane is preferred to use as silicon polymer in case of HV insulation, mainly for outdoor applications. 1. Compared to other organic hydrocarbon polymers, PDMS is of higher thermal and oxidative stability. Number 2, highly resistant to oxygen and ozone attack. Number 3, ability to perform a wider range of temperature, both high and low. Number 4, basically hydrophobic in nature. Number 5, attributing low surface energy. Number 6, better surface mobility with more or less non-adherent to dust but having susceptible in adhering oily pollutants. Polymer of low molecular weight. Number 8, low reactivity, toxicity, and combustibility. Number 9, excellent abrasion resistance. Number 10, excellent dielectric property. And number 11, rarely affected even at long-term exposures to UV rays, winds, or rain. With the recovery from hydrophilic characteristics to hydrophobicity and the specific phenomenon of transferring hydrophobicity to the surface pollution layer, the total process would have to make a water film having with formation of discontinuous small water droplets. As the water droplets stand separately over the surface and do not form a continuous film, it is most obvious that the bushing surface leakage current activity would have been restricted under sustained voltage action. Presence of these discontinuous small water droplets would have to cause very feeble electrical arc that to be distributed in a discontinued manner throughout the insulation surface. Because of less possibility of forming a concentrated type of leakage current discharge path, so chances of partial arc would not be easily developed and also have the less possibility of producing higher pollution flashover voltage. The state of hydrophobicity has thus opposed to have formation of continuous conducting water tracks on the insulation surface, which in turn would have to restrict the flow of surface leakage current activity and chances of pollution flashover. So, the major dielectric parameters is thus to be regained and then to be maintained for a longer time period while polymeric silicon rubber composed of polydimethyl siloxane is used for high voltage electrical insulators. However, any loss of hydrophobicity may have to influence subjective reduction in electrical insulation as well as the pollution withstanding performance, which ultimately has to propagate the aging process of the polymeric silicon rubber materials or insulators. Electrical and thermal properties of bushing insulation are closely related with the aging process, which is gradually developed within the long-term active power loss. Aging process of the insulating properties. It is also to be noted that the thermal state of the bushing will directly affect the electrical properties of the bushing insulator. Dielectric loss is an important parameter to characterize insulation condition of the bushing and for the cause of composite voltage configuration that may have to constantly aggravate the dielectric electrothermal effect inside the insulation. As of the structural features of the composite bushing, where the internal insulation distance of composite insulators is more or less equal to that of the external insulation part, and for which insulating properties of composite insulator is always be superior to that of porcelain insulator. Insulation dielectric losses that caused by conductivity and polarization under the effect of complex voltage waveform can also be extensively limited in case of composite insulation, and therefore subjective influence of aging process is thus to be restricted. Composite bushing can safely operate under the consequence of composite voltage, which includes power frequency, DC pulse, and other voltage components, that is superimposed voltage components. This type of bushing has to ensure safe operation under the most complex environment for a longer period and also may have to sustain usual performance parameter of the equipment insulation all through. Creepage distance is the measurement of shortest path along the surface of the insulating material between two conductive parts and obviously be a fundamental designing parameter of the bushing insulators for proper functioning. Creepage distance can also be characterized by the length of the leakage current flow path and thus to be referred in terms of millimeter per kV. In case of bushings, the creepage distance is the distance between the bushing top metallic terminal and the flange on which bushing is installed. See the diagram. The marked distance along the curved and straight portion of insulator is creepage distance or leakage distance. Mark distance is the dry arcing distance. Creepage distance of an insulator is the most important parameter which decide its electrical performance. So, during designing of a insulator, that you have to take some steps regarding creepage distance. Bushing with having adequate creepage distance that would facilitate to restrict the risk of certain electrical breakdown as and when an overvoltage condition occurs, which has thus to be initiated the voltage to arc over the insulation. While designing the insulator shed profile, the creepage distance for insulators must be met to justify certain basic criteria. 1. Rated phase to ground voltage. Number 2, degree of atmospheric pollution as follows. 1. A. Type of contaminants. B. Humidity. C. Corrosive chemicals. D. Altitude where the equipment is to be installed. Degree of atmospheric pollution is of much importance as because the dust particles always have a tendency to align to the direction of electrical field lines on the surface of the bushing insulators. Most important. Degree of atmospheric pollution is of much importance as because the dust particle always have a tendency to align to the direction of the electrical field lines on the surface of the bushing insulators. However, as of design, if the creepage distance would have been made adequate for bushing insulators, then there will be less possibility to form a continuous dust conducting track. Let's see. Degree of atmospheric pollution and recommended creepage distance for insulators as per guidelines IEC 60815. Number 1, if the area is clean, then 16 millimeter per kV creepage distance is sufficient. Moderately polluted areas, 20 millimeter per kV creepage distance. Highly polluted areas, 25 millimeter per kV. Areas of high contaminants, more than 31 millimeter per kV. As compared to porcelain bushing, the creepage distance of composite bushing insulators of the same voltage class is larger and the diameter of the shed profile is smaller. As stated in International Standard IEC 60383, the creepage distance also has tolerance and if needed, some additions can be provided. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedback inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.